Yeah. So first of all, let me thank the organizers for giving me this opportunity to talk in this session, remembering Paddy. Okay, it's a great honor to be invited to speak in this session, and it's also inevitable that I might be missing several things, several aspects of his work. So right at the outset, I would request you to excuse me if something has been missed. But on the other hand, what I'll try to do in this talk is take you through the immense breadth of Paddy's research work, which will also help you understand why it's inevitable that not all of it can be covered in a single talk. Okay? So let me begin. This is the plan of the talk. I would just start by talking about Paddy's academic legacy. This is largely well known, but I would also try to actually present it in a way which brings out his style of doing science, at least from my perspective. So the first two parts of the talk would be inevitably intermingled with each other. Okay? They are not separable. And then I'll go through a few of Paddy's papers from various epochs which Shanky just now spoke about. Try to make some comments on some of the work which has influenced our work, my work with Paddy, and some of the work which I've known was very close to his heart. He liked some aspects of the work which I'll comment on. Okay? And I will also indicate the broad interconnections between all these pieces of work, okay, which was one of hallmarks of Paddy's research. Okay? Finally, I'll conclude with some personal remarks and reminiscences. So it's only appropriate to start a lecture remembering Paddy with the so-called cube of theoretical physics, which I'm here terming as pyramid. It will become clear in the next slide why. And the reason is he liked to show this cube in many of his pedagogical introductory talks. And this broadly describes the landscape of physical theories with constants plotted on the axis. And like the quote from William Cooper there says, Paddy's work actually filled all parts of the cube. So I've just played around on his cube cartoon by instead taking a similar picture from an old paper by Kokash, which indicates the landscape of physical theories as a pyramid rather than the cube. But a point I'm trying to make is that Paddy worked in all of these areas. And not just that, he also indicated, highlighted, and found out interconnections between the various areas. And that is largely what I want to emphasize in this talk. Okay? And I hope that by the end of the talk, from going through his research work, something which is already evident to those who worked with him is the motto that excellence is not negotiable. And this is what Paddy said, came down largely through his family, circles. This is something which is indicated in the very nice biographical sketch in the volume Gravity and the Quantum, which was compiled on his 60th birthday. Some excellent articles, and the sketch by Jasjeet and Sunu provides a very nice overview of his personal as well as academic life. And the picture there, Paddy and the other one of his parents, is taken from a Malayalam weekly which was published just a few days within Paddy's passing away last year. Okay? I would indicate this as the last award which Paddy got when I come to the awards and distinction part of the talk. Okay? So before I move to the main part of the talk, I would just like to indicate a couple of, there have been many tributes and memorial lectures organized since last September, and I would just indicate a couple of them here. There is an article which I wanted to highlight. It's now a topical collection in general relativity and gravitation, a journal which was very close to Paddy's heart. So we have an excellent collection of 28 articles from various experts covering various domains of astrophysics, cosmology, gravitational physics, a wide domain of research work that interested Paddy. I would invite you to have a look at these articles. These are available on GRG website. And through IAGRG, we have also organized a one-day topical meeting on aspects called as aspects of emergent gravity, again in memorial of Paddy. And the speakers included possibly all the names that are very well recognized whenever the word emergent gravity is mentioned. Okay? We had Ted Jacobson, Mark Ramsdonk, Stefano Liberati, and Eric Verlinde speaking on this online workshop. These talks are also available on YouTube, and I invite you to have a look at them. Okay. There's also a collection of articles written by his students and close collaborators, which is available on the archive. And there are many other efforts which I might have skipped over the last year, and various talks, special sessions, conferences organized. But one thing that I wanted to start this talk with, and that is really the article which, my contribution to this article is a part of what was my PhD thesis acknowledgement in honor of Paddy, and by the time we come to the middle of the talk, it will become clear why this very aptly captures the glimpse of Paddy as a scientist whose insight, intuition, and the scientific breadth and depth actually helped him to avoid or see through the mathematical clutter and come right to the physical picture. As Paddy would term it, he would identify and tell you whether there is a basement to the building. That's his phrase. And the quote essentially is by Arnold. Arnold was speaking of a book by Isaac Barrow, which was written in a manner which most of the mathematicians found difficult to understand. And Arnold gives the reason for them finding it difficult to understand. I would leave it there for you to read, but I hope that it makes it clear that mathematical rigor and physical clarity is something which Paddy balanced very well. I would come back to this point when I mention Paddy's article on Subramaniam Chandrasekhar, organized in tribute to him, with a very tongue-in-cheek comment about how rigor for rigor's sake might actually work adversely in certain situations. Okay, so let me go ahead. Okay, and one quote which is often associated with Paddy has been mentioned several times in tribute to him is, and it also appears in the book which I mentioned, a collection of articles on his 60th birthday, is he always emphasized that theoretical physics is fun. Okay, and one instance of this is a talk he gave at Perimeter. He was supposed to give a talk summarizing his results on cosmological constant and emergent gravity, and around the same time he somehow found out that there was a newspaper article with Anna Hathaway saying that she is reading Einstein's theories and interested in string theory. She's interested in nature of space and time and stuff like that. And Paddy immediately wanted a cutout of that article, and this is how he started his talk at Perimeter. Of course, he was saying that quantum gravity, everybody wants to quantize gravity, even non-physicists would agree that it's an attractive problem. But the same can be said about theoretical physics on the whole. Okay, if you are curious what she was saying this. Okay, I don't have to emphasize it enough. Okay, so moving on, the aspect of theoretical physics being fun is what will be scattered throughout this talk, because that was scattered throughout Paddy's research work. I hope I am able to emphasize it throughout the talk. Okay, so I'll start by discussing some of his books, starting with pedagogical books, and then going on to mention the technical books that he has written. So Dawn of Science, it's a collection of articles on the history of science. These articles have been available for a long time in one form or the other, but more recently published as a book with Vasanthi. He has a popular science book on quantum themes describing the mysteries and non-trivial features of quantum mechanics. He has an excellent collection of articles on what he called as sleeping beauties in theoretical physics, articles or physical results that are sufficiently advanced but easy to convey at an undergraduate level. Okay, and even experts would find something new in this set of articles. And then the book which followed Steven Weinberg's first 3 minutes is after the first 3 minutes, where he describes work on structure formation and cosmology, and the title suggests after the first 3 minutes beginning of the universe. Okay. Coming to the technical part, Paddy wrote several books covering astrophysics, cosmology, and gravity, starting with a book on structure formation, a book on problems in cosmology and astrophysics, a book on theoretical astrophysics, which is just pitched at the right level. It's an invitation to theoretical astrophysics at a fairly technical level, but accessible at an undergraduate level. And then the famous 3-volume set on theoretical astrophysics, which was designed after the volume which he respected a lot, the Landau-Lifshitz series in theoretical physics, and the style is very much similar to that. Okay. His books on gravity, the theoretical aspects of gravity and field theories included a book which is relatively not that well known, starting with gravity, gauge theories, and quantum cosmology. There are some, the first time I encountered this book was in the library at IUCA, and it contains several nuggets, several results which are not found elsewhere, and some very deep insights into the structure of gauge theories and quantum field theories, apart from discussing GR and quantum cosmology extensively. Most recent books of his were Gravitation and Quantum Field Theory, again discussing a different way of thinking about both of these subjects with an extensive collection of problems and projects. Okay. Paddy wrote extensively. So the books, articles I've already indicated. He also wrote several reviews, starting, like Shanky said, summarizing his work with Professor Narlikar on quantum cosmology via path integrals, right till 2020, when he wrote about gravity, quantum theory, domains of conflicts and contact. And these were all interconnected, because if you actually stare at the list, it's not, sorry, okay, sorry. So if you actually look at the list, these reviews build upon several of his works which he has done in the past and thought about more afresh in recent time. For example, the last review he wrote also dealt with a work he did long back, right after his work on quantum cosmology. I'll indicate it with some comments. And a very rough statistic says that these reviews appeared roughly at a gap of 2.5 years, just indicating how prolific Paddy was, and also the topics were widely different. It covered all domains of astrophysics, cosmology, quantum gravity, and classical gravity as well. Okay. Paddy's scholarly achievements has been recognized through various awards and distinctions. The list is huge. Probably that's the only thing I can say about these couple of slides. He has received several awards, including Padma Shri, which was given by the President of India in 2007. And the last award, which he was supposed to receive in September 2021, the snapshot from the Malayalam Weekly is the one which sketched Paddy's profile in recognition for this award. And that's the snapshot I showed in the initial part of the slide. He has also received several awards in the Gravity Research Foundation essay contests, starting from, with certain commentary. As I said right in the beginning, it's inevitable that I might be missing several of his works, but I've just tried to take a sample from his broad research works with an intention that there's a common thread running through all of them, which I'll try to combine and make some comments on towards the end of this session. Okay. His very first paper was written while he was still an undergraduate. Okay. He was very proud of this paper. It appeared in Pramana, and what Paddy did was essentially take a metric produced by gravitational waves or electromagnetic wave, the so-called PP wave spacetimes, and solve the equations of scalar and electromagnetic waves in this geometry. Okay. Two things to highlight about this paper. If you just take a look at the end of the paper, after all the calculations are done, he concludes with the remark that it should be noted that these interactions discussed classically correspond to photon-graviton and photon-photon interactions in the quantized level. The QFT was not constructed at that time, but this was his broader outlook. This paper was written as a BSc student. I just wanted to emphasize that. And it had only one reference. The reference was to the classic textbook which Paddy used extensively to study GR, which is Misner, Thorne, and Wheeler. Okay, so that's all he needed to derive the results here. Next prominent work, which was his PhD work with Professor Narlikar, was quantum cosmology using path integrals, and this was actually a program, a huge program, which comprised of quantizing the conformal degree of freedom of metric, space-time metric. And there were some motivations, physical motivations for just quantizing the conformal degree of freedom and not the other components of the metric tensor. And Paddy was sort of not happy with it later down, as he once mentioned it to me. However, The insights coming from this actually got translated to some of his more recent work. Although this is restrictive, it still gives sufficient insight into some of the problems such as singularity resolution in quantum gravity. And this was commented upon, this is commented upon by the article by Professor Ashtikar et al. In the collected GRG volume, which I mentioned right in the beginning. Okay. One paper which he was extremely fond of in quantum cosmology was actually the paper where he discusses decoherence in the density matrix describing three geometries and the emergence of classical spacetime. And what Paddy did in this paper is he traced out the matter degrees of freedom in the solution of Wheeler-DeWitt equation and showed that the density matrix describing the three geometries can be written as a almost decoherent sum, and the decoherence was described by an exponentially decaying factor with the exponent depending on a measure of distance in the space of three geometries. Some work on this was done already by taking the measure of distance in terms of size or volumes of three geometries, but Paddy had a slightly more involved measure of distance where the eigenfrequencies of the Laplacian built out of these three geometries was also taken into account. Something very, very closely resembling the work that comes out by asking whether you can hear the shape of a drum, but that connection was never made by Paddy. However, he did have some interesting comments towards the end of this paper, which ended by the comment, probably ignorance is bliss. Because what Paddy was trying to say is that if you have lesser degrees of freedom to trace out, because the universe is expanding, if you have lesser and lesser degrees of freedom to trace out, you might be having a universe which is becoming more and more quantum as it's expanding. Of course, there is a catch in all this, but it's just something that again indicates his style of doing. So there's a very rigorous set of calculations followed by some speculative comments, which can be later built upon or refuted. Okay. Paddy also worked extensively in quantum field theory in curved spacetime, and one of the work which I wanted to highlight in this context was his work on accelerated detectors, and this is essentially got to do with things like Unruh effect. There was a large set of discussion involving papers by Unruh and Wald as to how Unruh effect looks as viewed from the inertial frame versus as it's viewed from an accelerated frame of reference. What exactly is the process which gives rise to the emitted quanta when a detector, a two-level simple detector, accelerates? And in typical Paddy style, he actually reduced the problem to an undergraduate level computation in quantum mechanics. What he analyzed was a very simple model of a detector comprising of two masses interacting with an external field, one of the masses interacting with the external field. And a very important comment in this paper, comment I found important, is he mentions that scalar field introduces an indirect coupling between the internal mode and the center of mass degrees of freedom. The reason this is important, it's very evident from the mathematical results that he presents, essentially results in time dependent first order perturbation theory. But the reason it is important in recent times is because this has gained attention from the point of view of universal decoherence caused by gravitational time dilation and stuff like that. Okay, it's not just Unruh effect. In fact, Paddy does not even discuss Unruh effect in this paper. He's just trying to find a mechanism where an accelerated detector can actually absorb energy from the accelerating potential, and the energy goes into both the center of mass degree of freedom and exciting the internal mode. Okay. He connects it with Unruh effect right at the end of that article. Okay. And just to indicate the breadth, perspectives and interconnections that Paddy followed in his research work, I wanted to also highlight a couple of his papers which are not that well known, and these are the papers on Mach principle and the notion of time and the role of Mach principle in quantum cosmology. Okay. And what Paddy did in these papers, they are very simple set of ideas. However, the connection was not made till Paddy mentioned it explicitly, and the idea was that usually Mach principle is formulated in terms of the statement that inertial frames locally are determined by the large scale distribution of matter in the universe. However, what Paddy emphasized is that time, the choice of time, plays a very crucial role in this formulation of Mach principle, even in the non-relativistic limit. And the choice of time is also what plays an important role in determining the quantum state of the field, something that was very much highlighted by the Fulling-Unruh effect that I mentioned about. So Paddy connected these two concepts and argued that Mach principle and notion of time, they are interconnected, and they might play, and this might play a crucial role in the field of quantum cosmology. And this is something different from the kind of research that I have discussed so far, but something which Paddy was extremely interested in, like Shanky also mentioned in his introduction, and this was statistical mechanics of gravitating systems, which culminated in the review which I have displayed here. So this actually proceeded in a few steps. I think the first thing which Paddy did, at least from what he told me once, was found a simple derivation of what is called as Antonov instability. So this is just that you put a bunch of self-gravitating particles in a box, and the equilibrium states of the system are determined by essentially the pressure exerted by the particles on the walls of the box and the strength of the gravitational interaction between the particles. So there are two relevant length scales in this problem: the size or the radius of the box taken as a sphere, and any short distance cutoff that you might introduce in your theory. Because the gravitational interaction is 1 by r, you have to introduce some cutoff to calculate finite thermodynamical quantities. And the results that were and the results that were known in this case was that depending on the range of parameters, the equilibrium configuration of the system is of the form of a dense core and a halo around it. However, there is an instability in the system unless the parameters are very carefully chosen. That is called as Antonov instability. If the density contrast is beyond a specific value, the numbers are weird, 709 or something like that. But if the density contrast is bounded by some specific number, then the equilibrium of the entropy does not have an extrema. Okay? And Paddy gave a very simple variational proof by finding the exact mode which causes the instability, essentially by solving the eigenvalue problem for the second variation of entropy. This again is a demonstration of combination of rigor and physical perspective, and this is where what I mentioned in the beginning of the talk about his comments on a couple of Chandra's work. So what Paddy highlighted was that Chandra could have discovered this instability way before Antonov did, simply by actually moving slightly away from his rigorous approach, analyzing the solutions of Lame-Amden equation for various isothermal sphere configurations, and making one simple plot on top of the plot that is already given in Chandra's book on stellar structure. Okay. The second thing he discusses in this article, which is right at the bottom, some curious history of Chandra's rare misses, also has to do with the interplay and balance of rigor and physical picture. And this has to do with Chandra's discovery of dynamical friction, which initially he missed, and which was actually contained in some of the older works by Landau. Okay. Once again, Paddy's claim was that Chandra employed rigor as a matter of policy, and if he had just taken that one step, he would have actually discovered dynamical friction right at the time when he was analyzing the kinetic theory associated with collision of stars in globular clusters. Okay. So this sort of summarizes his style of doing physics: combine mathematical rigor with the right emphasis on the physical picture wherever required. Okay. Paddy worked extensively on, he was very interested in the cosmological constant problem. That's the review which summarizes his earlier ideas, and at the end of the talk I would try to mention his most recent ideas on that topic. He worked a lot on how Planck scale or Planck length, existence of a lower bound on space-time intervals, affects quantum field theories and affects the structure of space-time. The earliest of his paper on this topic, which again he was extremely proud of, was the physical significance of Planck length. And he later built upon this by actually deriving modified Feynman propagator, which incorporates the existence of such a 0-point length, by introducing a new principle which he called as the principle of path integral duality. So if you postulate that relativistic action for a point particle should have certain inversion symmetry, then Planck length naturally appears in the Feynman propagator computed from the path integral of that relativistic action. And finally, the work which Paddy was largely focusing on over the past 10 to 15 years was associated with gravity and thermodynamics of horizons. And this also is it was his entry point into this formulation of gravity as an emergent phenomena. So I'll have more to say about this aspect of the work as we go along. Okay. The most recent of Paddy's thoughts on cosmological constant and gravity as an emergent phenomena is contained in his recent articles. These articles appeared in the last 5 to 10 years. Atoms of space, gravity, and the cosmological constant. As you would notice, this combines gravity, thermodynamics of horizons, as well as the incorporation of Planck length into the classical space-time picture, combining all of them and trying to get some results which are of observational significance, such as the explanation of value of the observed cosmological constant. Okay. So what I've mentioned so far would very clearly indicate that the research themes that Paddy was interested in largely involved around, well, all key focus areas of theoretical physics, but building largely upon two clues that have come from quantum field theory in curved space-time, that space-time can have thermal properties, and there is an operational limit to measurement of space-time intervals. Okay. The second one has to deal with Planck length as a 0-point length of space-time, a couple of references of which I have already mentioned. And the first one is actually identifying the true implication of the fact that space-time can have thermal properties, the interconnection between gravity and thermodynamics. Okay. So, and it is because this last topic was very much what he was focusing on towards the last 10 to 15 years. Let me mention a bit about it. Let me mention a bit about the emergent gravity paradigm. Okay. The idea is very old, starting from some of the works of Sakharov, various approaches by Damour, and Jacobson's work is going to play a key role, so I'm going to mention it again. Some ideas by Béla-Khou, some ideas by Wolowick coming from a condensed matter perspective, ideas on analog gravity by Wieser, Stefano Liberati, and others, and most recently popularized by the idea of entropic gravity by Verlinde. Okay. However, except for the work by Jacobson and Paddy, I am not going to discuss the other ideas in the emergent gravity paradigm. Okay. And before I indicate what Paddy's contribution was in this domain, I should just clarify that emergent gravity is a very, very broad umbrella term, and people use it to mean different things. When you talk about emergent gravity, you might be talking about gravitational dynamics emerging, that is just the equations of motion being interpreted or being derived as equations of thermodynamics, or the gravitational action emerging as an effective action with some thermodynamic interpretation, and finally the space-time itself emerging from some microscopic degrees of freedom. And Paddy had ideas on all these various aspects of emergent gravity paradigm, as I'll indicate in the next remaining few slides. Okay. Okay. So the idea of emergent gravity paradigm is basically very simple to state. It arises from the connection between gravity and thermodynamics. The connection arises from the fact that black holes Hawking radiate. And the second fact, which Unruh discovered, and I mentioned it as one of Paddy's work, is that accelerated detectors, even in flat space-time, would behave as if they are in a thermal bath at a temperature which is proportional to the acceleration. For those of you who don't know, this is called as the Fulling-Davis-Unruh effect. Okay. And combining all this, there is a deep connection between gravity and thermodynamics that has been discussed by Bekenstein, Hawking, and many other people. Okay. The idea was which led to a deeper perspective on gravity is that just like Einstein used his thought experiment involving the freely falling elevators to deduce that gravity should be described kinematically as a curved space-time, you can actually use Unruh effect, or if you like Hawking radiation, the thermal behavior of horizons in space-time. You can use this to deduce the dynamics of gravity. So kinematics of gravity follows from Einstein's elevator thought experiments. Dynamics of gravity can similarly be obtained using some analysis in quantum field theory that gives you things like Unruh effect. Okay. And Paddy's first work on this idea involves a very simple calculation. What he did was to just look at spherically symmetric geometries, something like a Schwarzschild geometry, all class of spherically symmetric geometry with horizon. Write down the time-time component of Einstein tensor. Doesn't look very covariant, but there is a covariant formalism. I'll just mention it in the next slide, so that's not a problem. Take the time-time component of Einstein tensor, write it at the horizon, and then you observe that by just multiplying and dividing with Planck constant here and there, you can write Einstein's equation as the equation of first law of thermodynamics, TdS minus d equals to PdV. This is the work which Sudipto, Asim and myself worked on for the initial part of our PhD. Okay. And it generalizes to a very large class of gravitational theories. It's not restricted to Einstein theory. So Einstein tensor was just a demo purpose thing. In the initial work with Sudipto, who is here, and Asim, he generalized it to a large class of gravitational theories called as the Lunkos-Lovelock models, which I'll indicate in the next slide. So it's something which is generic. I think we can fairly say that it's not something which is a curiosity of Einstein theory. It's something which is very generic, related to existence of horizons in space-time. Doesn't matter if the space-time is described by Einstein theory or some more general theories. Okay. That's the covariant version. You can take you can derive the full Einstein equations by just invoking by the time-time component, by invoking the democracy of all observers, which is inbuilt into GR. And that was the first clue which told Paddy that maybe gravity should be looked upon in the language of thermodynamics. And there was already in 95 work by Ted Jacobson, who very cleverly used the Rindler frames, local Rindler frames, to probe the thermodynamic nature, or to rather emphasize that gravity, Einstein field equations can be just related to equations of thermodynamics. Okay. His next clue into this was the fact that gravitation action functionals are holographic in nature. So what he essentially did was, for a large class of theories, again including the Lunkos-Lovelock models of gravity, he showed that the gravitational Lagrangian can be split as a surface term and a bulk term, and there is this precise relation between the surface and the bulk term, which was Paddy's version of holography inbuilt into gravitational theories. And the surface term was inherently linked, this you can compute and show, to the entropy associated with horizons if horizons are present in these space-times. Okay. So that again, this holographic structure combined with a thermodynamic interpretation for the surface term and also for the bulk term, I'll come to it in the next slide, indicated that maybe gravity can be formulated as a in the thermodynamic language. First part was equations of motion. The second bullet point here is about the action, and that's the second point in the taxonomy of emergent gravity models that I indicated a while back. Okay. Again, all of it generalizes to a wide class of gravitational theories, the one I keep mentioning, the Lunkos-Lovelock models of gravity. From this, Paddy then postulated, along with Asim, what he called as the entropy functional of space-time. And the idea was to replace the Einstein-Hilbert action with an entropy function. You don't vary the metric, you vary a vector field in this entropy functional, and as a constraint equations, you get back the equations of motion of the theory. Okay. Shanky, I have 5 minutes. Okay. So, in interest of time, I'll try to wind up the next few slides, but I am almost done. So, After this, Paddy actually postulated, combining all these insights, the idea of holographic equipartition, something that is being actively pursued now, which essentially said that gravitational field equations, if you have a space-time and if you introduce a certain foliation in space-time, gravitational field equations can be nicely written in terms of a difference between the surface and the bulk degrees of freedom. Like I mentioned in the previous slide, the surface degrees of freedom can be related to entropy associated with horizons in these spacetimes, so-called wall entropy in general. And the bulk degrees of freedom can be associated to energy density, which is called as the Komar energy density of spacetime. Okay? And this actually is the evolution law for a congruence, or the three volume, well, not three volume except in special cases, but evolution of geometrical quantities associated with the congruence in terms of number of degrees of freedom in the bulk and the surface. And of course, the final aspect of his work was implications for the cosmological constant problem. I'll briefly highlight this in the end. Okay. And the last bullet point in the taxonomy of emergent gravity models is the space-time itself emerging from microscopic degrees of freedom. And Paddy's insight here was that maybe we can construct a kinetic theory for the atoms of space-time. And this is where based on his work on duality and Planck scale effects in space-time, I was very tempted to add this section in my thesis, my PhD thesis, very speculative at that time, where basically we took the path integral duality seriously, and I tried to reformulate the metric of space-time, quote unquote metric, in terms of non-local quantities, such that the 2-point functions computed from that metric incorporates the Planck length naturally. And the final upshot, which took 10 years, of all this work was that we could postulate that the conventional description of space-time in terms of the metric need to be replaced by a description in terms of non-local quantities, the distance function to start with, but we brought in other non-local quantities, so-called bitensors, for those of you who are familiar with this. And very surprisingly, what we found that if you do this, there is a very intricate connection with the emergent gravity paradigm, in the sense that the action that you obtain by constructing this non-local geometry, what we called as the Q metric, is the action is something that reduces to the entropy functional, which was postulated by Paddy and which I displayed a few slides back. Okay? It doesn't reduce to the Einstein-Hilbert-Lagrangian, but to the entropy functional that Paddy had introduced in his earlier work with Asim. Okay? So I will end with that. Basically, I've just taken you through Paddy's work in emergent gravity paradigm largely. I hope I've emphasized other aspects of his work as well. But so the emergent gravity aspect at least started from taking clues from semi-classical gravity and try to see whether, without invoking any of the frameworks, without tying yourself to specific framework of quantum gravity, what can the ideas based on emergent gravity say about the small scale structure of space-time, and specifically about whether it can give you any new insights into dynamics of GR at low energies. So this was all about introducing Planck length and this and that, but if it can say something about GR at low energies, that will be the most desirable. And essentially this is like asking if the hints of emergence are in plain sight. So towards the end, two main questions in this domain was cosmological constant and space-time singularities. His most recent ideas of cosmological constant were in work with Hamza. I would not go in any more detail here. I'm already out of time, I guess. What remained was the discussion of space-time singularities, and unfortunately, we do not have, it's difficult with Paddy's insight, intuition, and breadth of knowledge. They were key in developing or using the mathematical formalism to address these deep problems. It will be difficult without his insights available. Okay. And before I end, this was just one point. Just a day before he passed away, we were discussing something called as the river metric in GR. It's more of a personal reminiscence. And this is also something which I started my graduate school project with. Okay? So in retrospect, it seems like it came full circle. And some of the final thoughts, which I will leave it here for you to read, But I would just like to read out one statement from here, is that Paddy's style infused a certain strength to pursue paths which are less fashionable in search of fresh insights. And one finds an echo of this in the remark from his homepage, where he is talking about structure formation and some aspects of it, some tools used there. And what he mentions is, though progress has become very difficult in recent years in this area, since the area has become fashionable. Okay, I think that gives sufficient hints as to this. So in the end, let me just indicate, for those of you who are Star Wars aficionado, the picture is enough to convey what I want to convey. Other than physics, Paddy also had answers to other aspects of life, and you can have a look at his webpage. There is an answer. If you are curious, if you have not looked at it, I would encourage you to read it. And I will end with this slide, which again contains a quote from Paddy. Unlike Yoda, he did have answers to other questions of life as well, but I want to end with this slide. Okay? Yeah. Thank you. Thank you for listening.
Thanks, Dawood, for excellent talk about Paddy's work. If there are any comments, or if there are. Yeah, question. Okay.
So what about Paddy's thoughts on gravitational waves, and after the LIGO discoveries, was he excited enough? And
Was he excited enough about gravitational waves?
To work on it? And
well, I haven't interacted with him on gravitational waves. Maybe Kinjalk or Sumanto can mention, but I haven't heard him discuss about this, at least in our discussions. Okay, so if he was like, I would imagine he would definitely be excited about it, but whether he was planning to do some work along those lines is something I don't know. I don't think so. Yeah. Okay.
I don't know what he meant by excited enough. So.
Yeah. Well. So you said it. Yeah. I don't think I can answer that. Yeah.
Yeah. So I mean, whatever the interactions which I had with Paddy about gravitational waves, I mean, he was not surprised that they are detected. I think he always thought that there would be detections, and and he always sort of was looking forward to what all things you will detect. So I think that is.
Thanks, Archana.
Yeah, thanks again for Dawood, and thanks to all of you to be here. And